There is a moon orbiting Jupiter right now that has no right to exist the way it does. Its surface is younger than most buildings on Earth. It erupts with such fury that lava fountains climb dozens of miles into a vacuum sky. Its mountains are taller than anything on our planet, yet they were not built by volcanoes. They were squeezed upward by a crust being crushed from below. There are no impact craters anywhere on its surface, not because nothing has ever hit it, but because the evidence is erased as fast as it forms. This is Io. A world roughly the size of our own moon, trapped inside the most punishing gravitational system in the solar system. And the violence never stops. If this kind of deep science is what you come here for, go ahead and hit like and subscribe. It helps more than you know, and it keeps stories like this one coming. Are you comfortable? Let's begin. In 1610, a man in Padua pointed a homemade telescope at Jupiter and noticed something that should not have been there. 3 small points of light, sitting in a line beside the planet. The next night, they had moved. The night after that, they had moved again. Within weeks, Galileo Galilei had identified 4 distinct objects circling Jupiter, and in doing so, he shattered a belief that had governed astronomy for more than 1,000 years. Not everything in the sky revolved around the Earth. Some things revolved around other worlds. Those 4 objects became the most famous moons in history. Ganymede, the largest moon in the solar system. Callisto is one of the most heavily cratered objects ever observed. Europa, a frozen world hiding what may be a liquid ocean beneath its shell. And Io, the innermost of the 4, a name pulled from Greek mythology. A priestess loved by Zeus, the very god the planet Jupiter was named after. For more than 350 years after Galileo's discovery, Io remained a point of light. Astronomers could track its orbit. They could measure its brightness. They could calculate its mass from its gravitational influence on the other moons. But they could not see its surface. They could not know what kind of world it was. And because no one could see it clearly, everyone assumed it looked the way moons were supposed to look. Grey, quiet, pockmarked with ancient craters, geologically dead, a frozen relic from the formation of the solar system sitting obediently in orbit, around something much larger. That assumption held for centuries. It survived the invention of better telescopes. It survived the first spectroscopic studies of Jupiter's system. It survived the Pioneer 10 and Pioneer 11 flybys in 1973 and 1974, which provided improved mass estimates and confirmed that Io was dense, composed of silicate rock rather than ice, unlike many moons of the outer solar system. The density was unusual, but it did not trigger alarm. A rocky moon orbiting a gas giant was unexpected, but it was not threatening to any existing theory. It was simply filed away as an oddity. Then came 1979. On March 5th of that year, the Voyager 1 spacecraft completed its closest approach to Jupiter and turned its cameras toward Io. The images that came back did not look like a moon. They did not look like anything anyone had ever seen in the solar system. The surface was vivid. Patches of yellow, orange, white, red, and black covered the terrain in patterns that resembled nothing so much as a diseased wound. There were no impact craters, not a single confirmed one anywhere on the visible surface. In a solar system where every solid body from Mercury to Callisto bore the scars of 4.5 billion years of bombardment, Io's face was clean, unnaturally, disturbingly clean. The implication hit immediately. Something was erasing the craters. Something was covering the surface faster than impacts could mark it, and whatever that something was, it was happening right now. The confirmation came from an unlikely source. Linda Mora Beto, a navigation engineer at the Jet Propulsion Laboratory, was processing Voyager 1 images to refine the positions of Jupiter's moons for trajectory planning. She was not looking for geological discoveries, she was doing math. But when she examined one image taken as Voyager looked back at Io after the flyby, she noticed a strange crescent-shaped feature extending off the edge of the moon's disk. It was enormous. It rose hundreds of kilometers above the surface, and it was not part of the moon's solid body. It was a plume, a volcanic plume, caught in the act of erupting, frozen in a single frame of Voyager's camera. It was the first confirmed active volcanic eruption ever observed on any world other than Earth. Within days, the Voyager imaging team identified more. Not one or two, but at least 8 active volcanic eruptions visible in the flyby data. 8 eruptions happening simultaneously on a world roughly the size of Earth's moon. The reaction inside the Jet Propulsion Laboratory was unlike anything the Voyager imaging team had experienced. These were scientists accustomed to surprises. They had already processed extraordinary images of Jupiter's atmosphere, its rings, and the surfaces of the other Galilean moons. But the Io images produced something closer to disbelief than excitement. The initial photographs were so unlike any moon surface ever observed that some team members questioned whether the camera was functioning correctly. The colors were wrong. The textures were wrong. The complete absence of impact craters on a world that should have been saturated with them made no geological sense under any existing model. Edward Stone, the Voyager project scientist, later described the discovery of active volcanism on Io as the biggest surprise of the entire Voyager mission. A finding so far outside existing models that it redefined what the scientific community believed was possible on a small world. And this was a mission that had already rewritten textbooks on atmospheric dynamics, ring systems, and satellite geology before it even reached Io. The confusion deepened as the team processed more images. Some features looked like volcanic calderas, but at scales far larger than anything on Earth. Others looked like vast frozen floods of material, smooth plains that appeared to have been liquid and then solidified. The color palette, sulfurous yellows, burnt oranges, stark whites, and jet blacks, suggested chemistry unlike any planetary surface ever studied. Several researchers initially proposed that the colors might be artifacts of the imaging process, errors introduced by the way Voyager's cameras handled the specific wavelengths reflected by Io's surface. They were not artifacts. The colors were real, and they were the visual signature of a world covered in sulfur, sulfur dioxide, and silicate lava in every stage of eruption, cooling, and chemical transformation. What made the scientific shock even greater was the timing of the Peel, Casson, and Reynolds paper. The prediction of tidal heating and active volcanism had been published in Science just 3 days before the flyby. Most of the Voyager team had not read it. The paper existed in the literature available to anyone, and it had correctly predicted exactly what Voyager found. But the prediction was so far outside the mainstream understanding of how moons behaved that it had not penetrated the consciousness of the imaging team before the images arrived. The confirmation came not as a vindication of a widely anticipated theory, but as a collision between an obscure theoretical prediction and an overwhelming observational reality, both arriving in the same week, neither prepared for the other. The surface that had seemed so bizarre in the first images suddenly made sense. The wild colours were sulfur and sulfur dioxide frost in various thermal states. The smooth plains were lava flows, some still warm. The dark spots scattered across the surface were volcanic vents, calderas, and active lava lakes. The reason there were no impact craters was not that Io had avoided being hit. It was that the entire surface was being replaced so rapidly that no crater could survive long enough to be recorded. Io was not dead. Io was the most volcanically active body in the entire solar system. And it was not even close. To understand why this discovery was so shocking, you need to understand what scientists believed about moons at the time. In 1979, the dominant model of moon geology was based almost entirely on one example: our moon. Earth's moon is roughly 3,474 kilometers across. It formed approximately 4.5 billion years ago. It was volcanically active in its early history, producing the dark basaltic plains visible from Earth called Maria. But that activity ended more than 1 billion years ago. The moon today is geologically dead. Its interior has cooled. Its surface changes only when something hits it from the outside. It is a museum of impacts, preserving craters from every era of the solar system's history in exquisite detail. This was the template. Moons were supposed to be cold, still, ancient. The smaller a body, the faster it radiated its primordial heat into space, and the sooner its geological engine shut down. A world the size of Io, with a diameter of roughly 3,643 kilometers, only slightly larger than Earth's moon, should have been dead for billions of years. Its internal heat should have been long gone. There should have been nothing left to drive volcanism. But Io was not following the template. Io was erupting everywhere, all the time, with a violence that dwarfed anything on Earth. The question that consumed planetary scientists in the weeks and months after the Voyager 1 flyby was immediate and unavoidable. Where was the energy coming from? The answer, it turned out, had already been published. 3 days before Voyager 1 reached Io, a paper appeared in the journal Science by Stanton Peele, Patrick Casson, and Ray Reynolds. Using orbital mechanics and tidal theory, they had calculated that Io should be experiencing intense internal heating, caused by the gravitational interaction between Jupiter and the other Galilean moons. They predicted that Io's interior would be partially or entirely molten. They predicted active volcanism. They predicted it before anyone saw it. The timing of that paper is one of the great coincidences in the history of planetary science. The theory and the observation arrived within the same week, and together they revealed something about Io that would take decades to fully appreciate. This was not a moon with a volcanic problem. This was a moon whose entire existence was defined by a gravitational punishment it could not escape. But to understand that punishment, you first have to understand how different Io is from the worlds that orbit alongside it. Jupiter has 4 large moons, the Galilean satellites, and they could hardly be less alike. Callisto, the outermost, is a portrait of stillness. Its surface is one of the oldest in the solar system, saturated with impact craters layered on top of one another across billions of years. Callisto has changed so little over time that scientists use it as a reference point for what an undisturbed icy body should look like. Its interior shows little evidence of significant geological activity. It may not even be fully differentiated, meaning its rock and ice may never have fully separated into distinct layers. Callisto is what a moon looks like when the universe leaves it alone. Ganymede, the next one inward, is more complex. It is the largest moon in the solar system, bigger than the planet Mercury, and it is the only moon known to generate its own magnetic field. Its surface shows two types of terrain. Dark, ancient, heavily cratered regions sit alongside lighter, younger, grooved terrain that shows evidence of past tectonic activity. Ganymede has been worked on by internal forces, but those forces appear to have faded. The grooved terrain is old. The geology is largely quiet now. Ganymede had a chapter of violence in its past, but it has moved on. Europa, the next inward, is something else entirely. Its surface is a shell of water ice, cracked and refrozen in patterns that suggest an ocean of liquid water exists beneath. That ocean, kept warm by tidal heating from Jupiter, is one of the most compelling environments in the solar system for the search for life. Europa's surface is young by geological standards, perhaps only 40 to 90 million years old in places, indicating that the ice shell is being reworked from below. Europa is active, but its activity is hidden. It is a world of internal secrets, wrapped in a frozen skin that conceals whatever is happening underneath. And then there is Io. Io is the innermost of the four. It orbits closer to Jupiter than any of them, and it is the one that Jupiter has broken. Where Callisto is still, Io is in constant motion. Where Ganymede's activity belongs to the past, Io's activity is happening right now, every hour, every day, without pause. Where Europa hides its energy beneath ice, Io puts everything on display. Lava lakes, erupting vents, sulfur plumes climbing hundreds of kilometers into space, mountains being thrust upward by a crust that is being crushed from below. There is no hiding on Io. The violence is the surface. The numbers are staggering. As of the most recent surveys, scientists estimate that Io hosts approximately 400 active volcanoes, not 400 volcanic features, 400 active sources of eruption on a world whose entire surface area is smaller than the continent of Africa. The heat radiating from Io's interior is approximately 100 trillion watts. Earth, a planet with roughly 12 times Io's surface area, produces roughly 44 trillion watts of internal heat. Io, a moon roughly the size of Earth's moon, is outproducing the entire planet Earth in geological heat output. Per unit of surface area, the difference is not subtle. Io's heat flux is roughly 1 to several watts per square meter. Earth's average geothermal heat flux is approximately 0.09 watts per square meter. Io is generating roughly 20 to 40 times more heat through every square meter of its surface than the planet you are standing on. And a 2026 study based on thermal data from NASA's Juno spacecraft suggested that even these extraordinary figures may be too low. When researchers accounted for the thermal contribution of cooler crustal regions that earlier instruments had overlooked, the implied total heat output climbed by as much as an entire order of magnitude. The violence pouring out of Io may be 10 times greater than the numbers scientists had been working with for decades. The resurfacing rate tells the same story from a different angle. On Io, new volcanic material covers the surface at an estimated rate of roughly 1 centimeter per year, averaged globally. That does not sound dramatic until you consider what it means over time. Every million years, the entire surface has been buried under approximately 10 kilometers of new material. Every 10 million years, 100 kilometers. Io has been volcanically active for billions of years. The surface you see today, the reds, the yellows, the black calderas, the white sulfur dioxide frost, none of it is old. The oldest exposed terrain on Io is estimated to be no more than a few million years at most. In a solar system filled with ancient surfaces preserving the scars of primordial bombardment, Io's face is brand new. It is a world that destroys its own history as fast as it creates it. Voyager 2 confirmed and extended the findings 4 months later when it flew through the Jupiter system in July of 1979. Several of the eruptions observed by Voyager 1 were still active. Some had changed, new ones had appeared. The surface had already been modified in the short interval between the two flybys, providing direct visual evidence of the resurfacing process in action. In the years and decades that followed, every spacecraft that visited the Jupiter system confirmed and deepened the picture. The Galileo orbiter, which operated from 1995 to 2003, made multiple close flybys of Io and returned the most detailed images of its surface ever captured. Galileo revealed lava temperatures exceeding 1,800 degrees Kelvin in some eruptions, far hotter than any active lava on Earth today, and consistent with ultramafic magma compositions, similar to the ancient lava flows that built some of Earth's earliest continental crust. It documented the behavior of Loki Patera, a lava lake roughly 200 kilometers across, larger than Lake Ontario, that periodically brightens and dims as its solidified crust overturns and exposes fresh, molten rock below. Galileo watched plumes erupt, watched surface colors change, watched new dark deposits appear around vents that had not been active during previous orbits. One of Galileo's most significant findings concerned the temperatures of Io's lavas. Ground-based infrared observations had suggested high temperatures, but Galileo's near-infrared mapping spectrometer measured thermal emissions from several eruption sites that implied magma temperatures exceeding 1,800 Kelvin. This was far hotter than any active lava on modern Earth, where basaltic eruptions typically reach approximately 1,400 to 1,500 Kelvin. Temperatures in the 1,800 Kelvin range and above are consistent with ultramafic compositions, magnesium-rich silicate melts, similar to the Komatiite lavas that erupted on Earth more than 2 billion years ago during the Archean Eon, when our planet's mantle was substantially hotter than it is today. The implication was striking. Io's interior was being heated so intensely by tidal forces that it was producing lava compositions that Earth itself had not generated in over 2 billion years. The tidal engine was not merely keeping Io warm, it was driving temperatures in certain magma chambers to levels that exceeded anything in the modern terrestrial volcanic record. Io was not performing for the cameras, it was simply doing what it always does. More recently, NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, conducted extremely close flybys of Io in December of 2023 and February of 2024, passing within approximately 1,500 kilometers of the surface. These were the closest approaches to Io since Galileo, and they returned some of the most detailed data ever collected on the moon's gravity field, surface features, and volcanic behavior. In January of 2025, the Juno team announced the detection of the most powerful volcanic eruption ever recorded on Io. An event so intense that it overwhelmed the spacecraft's infrared instrument and forced scientists to revisit their assumptions about how much energy a single eruption on this moon could release. And in November of 2025, the James Webb Space Telescope added its own layer to the story, capturing infrared observations of Io that revealed vigorous eruptions, revealed new sulfur chemistry in the atmosphere, and showed thermal variability across multiple volcanic sites. The Webb data confirmed that Io's volcanic output is not declining. It is not cycling down. It is continuous and intense, driven by forces that show no sign of weakening. Here is what makes Io fundamentally different from every other geologically active world we know. Earth is volcanically active because of its internal heat, generated by radioactive decay and residual primordial energy, driving plate tectonics and mantle convection. That heat is real, but it is finite. Earth is slowly cooling. Its geological engine will eventually wind down over billions of years. Venus, Mars, Mercury, our moon, they have all already cooled past the point of significant volcanic activity. Their engines are off. Io's engine is not internal in the same way. Io's heat does not come from radioactive decay or primordial energy. It comes from outside. It comes from Jupiter. It comes from the gravitational geometry of Io's orbit, locked in a resonance with Europa and Ganymede that prevents the orbit from ever becoming circular, forcing Io to flex and deform with every revolution, generating frictional heat that melts its interior and drives its volcanism from the top of its crust to whatever depth the magma chambers reach. Io cannot cool down. Its heat source is not inside it, waiting to be exhausted. Its heat source is the orbit it follows, the planet it circles, and the moons it is locked in step with. The engine is gravitational, and gravity does not run out of fuel. That distinction is the key to everything that follows. Because what Jupiter is doing to Io is not simply producing volcanoes. It is producing a world that has no path to geological peace. A world where the internal stress is permanent, the surface is disposable, the mountains are built by compression and destroyed by eruption, and every feature you see is a temporary symptom of an underlying condition that will never resolve. The mechanism behind that condition has a name. It is called tidal heating, and the orbital architecture that sustains it, the Laplace resonance, is one of the most elegant and most punishing gravitational arrangements in the known solar system. Understanding how it works is the only way to understand why Io is what it is. And what it reveals about the forces acting on this moon is far more violent than the surface alone suggests. To understand what is happening to Io, you have to stop thinking about volcanoes. Volcanoes are the symptom. The disease is orbital. It lives in the geometry of how Io moves around Jupiter, how Europa moves around Jupiter, and how Ganymede moves around Jupiter. The three of them are caught in an arrangement so precise and so inescapable that it has been forcing Io's interior to melt for billions of years. And unless something catastrophic disrupts the system, it will continue doing so for billions more. The arrangement has a name. It is called the Laplace resonance, after the French mathematician Pierre-Simon Laplace, who first described the orbital relationship in the late 1700s. The mathematics behind it are elegant. The consequences for Io are brutal. Here is how it works. Io orbits Jupiter once every approximately 42.5 hours. Europa, the next moon outward, orbits once every approximately 3.5 Earth days. Ganymede, the next one beyond that, orbits once every approximately 7 Earth days. If you do the arithmetic, a pattern emerges. For every single orbit Ganymede completes around Jupiter, Europa completes almost exactly 2. and for every single orbit Europa completes, Io completes almost exactly 2. The full ratio across all 3 moons is 4 to 2 to 1. Io circles Jupiter 4 times in the same period that Ganymede circles it once. This is not a coincidence. It is a resonance. The 3 moons are gravitationally locked into this ratio by billions of years of tidal evolution. Their mutual gravitational interactions reinforce the timing. Every time Io laps Europa, the 2 moons are at the same relative position. Every time Europa laps Ganymede, the same thing happens. And the Laplace resonance adds one more constraint on top of the pairwise relationships. The 3 moons are arranged so that they can never all be on the same side of Jupiter at the same time. Their longitudes are locked in a configuration that prevents triple conjunction. If Io and Europa are close together, Ganymede is on the opposite side of its orbit. The system is perpetually staggered, perpetually tugging, perpetually preventing any one of the 3 from settling into a simpler, quieter orbital state. The natural question is how the resonance came to exist in the first place. Io, Europa, and Ganymede did not form in this precise 4 to 2 to 1 ratio. The resonance was assembled over time by the same tidal forces that now sustain it. The process begins with Jupiter itself. Jupiter rotates rapidly, completing 1 full rotation approximately every 10 hours. That rotation rate is faster than the orbital period of any of the Galilean moons. When a planet rotates faster than its moon's orbit, the tidal bulge that the moon raises on the planet is carried slightly ahead of the moon by the planet's rotation. This offset creates a gravitational torque that transfers angular momentum from the planet's spin to the moon's orbit. The result is that the moon spirals slowly outward, its orbital radius increasing over geological time. Io, being the closest of the 4 large moons to Jupiter, experienced this outward migration most strongly. As Io migrated outward, its orbital period lengthened. At some point, Io's period reached a value where it was exactly half of Europa's period. The 2 moons were now in a 2 to 1 resonance. The gravitational kicks at each conjunction reinforced the orbital timing, locking the 2 moons into the resonant ratio. Once locked, the resonance itself began to drive Europa outward. The angular momentum being fed into Io's orbit by Jupiter was now partially transmitted to Europa through the resonant coupling. Europa migrated outward as well, its period lengthening until it reached a value where it was exactly half of Ganymede's period. A second 2 to 1 resonance engaged. The full Laplace configuration, 4 to 2 to 1, was established. The entire process likely took hundreds of millions of years. It was not sudden. It was not dramatic. It was the slow, grinding accumulation of tiny gravitational nudges over epochs so long that continents would have formed and eroded multiple times on Earth during the same interval. But the end result was permanent. Once all 3 resonances were locked, the system stabilized. The energy input from Jupiter's rotation continuously maintains the configuration, replacing whatever orbital energy is lost to tidal dissipation within the moons. The trap did not spring shut in an instant. It built itself, 1 orbital nudge at a time, across a span of time that dwarfs recorded history by a factor of tens of thousands, and once it was complete, it held. This origin story matters because it reveals something important about the nature of Io's predicament. The resonance was not imposed by a catastrophic event. There was no collision, no capture, no sudden rearrangement. The system evolved naturally, inevitably, through the ordinary operation of tidal physics. If you replayed the history of the Jovian system with slightly different initial conditions, the details might differ, but the general outcome would likely be the same. Tidal migration drives moons outward. Resonances capture them. The Laplace configuration, or something like it, is a probable outcome of the long-term tidal evolution of any system of large moons around a rapidly rotating giant planet. Io's trap is not a freak accident. It is a natural consequence of the physics that governs planetary systems. The violence was always coming. This matters for Io because of one critical consequence. The resonance forces Io's orbit to remain slightly elliptical, not dramatically elliptical. Io's orbital eccentricity is only about 0.004. That is nearly circular. But nearly is not the same as perfectly. And the difference between nearly circular and perfectly circular is the difference between geological death and the most violent moon in the solar system. If Io's orbit were a perfect circle, it would maintain a constant distance from Jupiter at every point in its revolution. The gravitational pull from Jupiter would be steady and unchanging. Io's shape would settle into a fixed, slightly elongated form, its near side pulled a little closer to Jupiter than its far side, and that will be the end of the story. No flexing, no friction, no heat, but Io's orbit is not a perfect circle. Because of the resonance with Europa and Ganymede, the orbit has that tiny eccentricity. And that eccentricity means Io's distance from Jupiter changes during every single revolution. At its closest approach, Io is roughly 420,000 kilometers from Jupiter's center. At its farthest, roughly 423,400 kilometers. The difference is only about 3,400 kilometers. On the scale of Jupiter's system, it is minuscule. On the scale of what it does to Io, it is catastrophic. Jupiter is massive. It contains more mass than all the other planets in the solar system combined. Its gravitational field is enormous, and it falls off rapidly with distance according to the inverse square law. When Io is 3,400 kilometers closer to Jupiter, the gravitational pull on its near side versus its far side is measurably stronger than when it is 3,400 kilometers farther away. That difference in pull creates a difference in the tidal force acting on Io's body. Think of it this way. Imagine you are holding a rubber ball and squeezing it. If you squeeze it once and hold that pressure steady, the ball deforms and stays in its new shape. No energy is generated, no heat is produced. But if you squeeze and release over and over again, the ball heats up. The repeated deformation generates friction inside the material. The faster you squeeze and release, and the harder each squeeze is, the more heat you produce. Now imagine doing this to an entire world, a sphere of rock and metal nearly 2,000 kilometers in radius, squeezing and releasing it every 42.5 hours, with the hand doing the squeezing belonging to the most massive planet in the solar system. That is tidal heating, and that is what Jupiter does to Io on every single orbit. The tidal bulge on Io, the physical deformation of its solid body caused by Jupiter's differential gravitational pull, is extraordinary. At the extremes of its orbit, Io's surface rises and falls by as much as approximately 100 meters. To place that in perspective, Earth also experiences solid body tides from the Moon and the star we orbit. Those tides deform Earth's surface by roughly 20 to 30 centimeters. Io's tidal deformation is roughly 300 to 500 times greater. And it happens on every orbit, without pause. Every 42.5 hours, the entire solid body of Io is stretched toward Jupiter at closest approach, relaxes slightly as the distance increases, and then is stretched again as it returns. The rock flexes, the interior heats, the magma rises, but the word friction, while useful as a shorthand, obscures what is actually happening inside the rock at the material level. Io's interior is not generating heat the way two surfaces rubbing together generate heat. The process is more subtle and in some ways more relentless. When a solid body is cyclically deformed, as Io is during every orbit, the mechanical energy of that deformation is absorbed at the microscopic scale, at grain boundaries within the crystalline structure of silicate rock, at tiny fractures too small to see, and in regions where the rock is warm enough to behave partly as a viscous fluid rather than a rigid solid. The repeated stretching and compression converts orbital energy into thermal energy. Physicists call this anelastic dissipation. It is the same process that causes a metal wire to grow warm when you bend it back and forth rapidly. The energy does not appear at the surface. It appears inside the material, at the boundaries between crystals, at the edges of microscopic imperfections, in every zone where the structure of the rock resists deformation and then yields. What makes this process especially punishing for Io is that it feeds on itself. Anelastic dissipation is most efficient in rock that is already warm, rock that is approaching its melting point and has begun to soften. Cooler, more rigid rock resists deformation more effectively and absorbs less energy. Warmer, partially weakened rock deforms more readily and converts more mechanical energy into heat. This means that as tidal flexing heats a region of Io's mantle, that region becomes better at absorbing further tidal energy, which heats it more, which makes it even more efficient at absorbing energy. The process accelerates in exactly the zones where melt is beginning to form. Io's interior does not simply warm uniformly. It develops runaway hot zones, regions where the feedback between heating and dissipation concentrates energy until magma chambers are born. This is the engine that Stanton Peele, Patrick Casson, and Ray Reynolds identified in their 1979 paper, published 3 days before Voyager 1 confirmed it. Their calculation was based on the known orbital parameters of the Galilean moons and the estimated rigidity of Io's interior. They showed that the energy generated by tidal flexing was more than sufficient to melt a significant fraction of Io's interior and drive sustained volcanism. They were right. The eruptions Voyager found were exactly what the physics predicted. But what makes Io's situation truly inescapable is not the tidal heating itself. It is the reason the heating never stops. And that reason leads back to the resonance. In most orbital systems, tidal forces work to circularize orbits over time. When a moon flexes due to tidal forces, the energy that heats its interior has to come from somewhere. It comes from the orbit. Specifically, it is extracted from the moon's orbital energy, which causes the orbit to evolve. In a simple two-body system, a planet and a single moon, tidal dissipation would gradually drain the eccentricity from the moon's orbit, making it more and more circular. As the orbit circularized, the tidal flexing would decrease, the heating would diminish, the volcanism would wind down. Eventually, the moon would settle into a perfectly circular orbit and go quiet. This is what happened to Earth's moon. Early in its history, our moon likely experienced significant tidal heating from Earth. Its orbit was more eccentric. It was closer. The tidal forces were stronger. But over billions of years, the orbit circularized. The heating stopped. The moon's geological engine shut down. This is the normal outcome. Tidal heating is supposed to be a temporary phase, not a permanent condition. Io does not get that outcome. The Laplace resonance prevents it. Every time tidal dissipation tries to drain eccentricity from Io's orbit, the gravitational kicks from Europa pump it back in. Europa, in turn, has its eccentricity maintained by Ganymede. The three-body resonance acts as a feedback loop. Energy is extracted from Io's orbit by tidal heating, and the resonance replenishes the orbital eccentricity that makes the heating possible. The cycle does not wind down. It sustains itself. The ultimate energy source powering this entire system is Jupiter's rotation. Jupiter rotates once every approximately 10 hours, far faster than any of the Galilean moons orbit. Tidal interactions between Jupiter and the moons gradually transfer angular momentum from Jupiter's rotation to the moon's orbits, pushing them slowly outward over geological time. This transfer is what maintains the resonance and keeps the eccentricities locked in place. Jupiter is so massive and rotates so quickly that this energy reservoir is, for all practical purposes, inexhaustible on timescales relevant to the solar system's remaining lifetime. Jupiter will not spin down enough to release Io from its torment before the star above exhausts its fuel billions of years from now. This is the trap. Io cannot circularize its orbit. It cannot stop flexing. It cannot stop heating. It cannot stop erupting. The resonance is locked. The energy source is effectively infinite. And every 42.5 hours, the cycle begins again. Now, a reasonable question arises. If we know the mechanism, if we know the tidal heating is melting Io's interior, what exactly does that interior look like? For decades, the most widely discussed model was dramatic. Many scientists believed that Io harbored a global magma ocean, a continuous layer of molten rock sitting just beneath the crust, fed continuously by tidal dissipation and serving as a single, connected reservoir for all of Io's volcanic activity. The idea had a certain elegance. If tidal heating was this extreme, surely the interior had been melted into one vast interconnected system. The volcanism was so widespread and so intense that it seemed to demand a source that was equally vast and interconnected. Some observational evidence supported this picture. Data from the Galileo spacecraft's magnetometer, which measured how Io interacted with Jupiter's magnetic field, suggested the presence of a highly conductive layer beneath the surface. Molten silicate rock is electrically conductive. A global layer of it would explain the magnetic signature. Thermal models also showed that the amount of heat Io was producing was consistent with a partially or fully molten layer in the upper mantle. But the question was never fully settled by Galileo's data. The magnetic evidence was suggestive, not conclusive, and alternative models existed. Some researchers argued that Io's heat could be transported to the surface through a network of localized magma bodies, individual chambers and conduits feeding individual volcanoes, without requiring a global connected ocean. These models were harder to reconcile with the sheer volume of heat being produced, but they were not ruled out. In December of 2024, the debate took a decisive turn. A paper published in the journal Nature, led by Ryan Park at the California Institute of Technology, and based on data from NASA's Juno spacecraft, presented the strongest evidence yet against the global magma ocean hypothesis. The key data came from the two closed Juno flybys described earlier, which passed near enough to Io to measure its gravitational influence on the spacecraft with extraordinary precision. The technique was gravitational. As Juno flew past Io, the moon's gravity slightly altered the spacecraft's velocity. Those changes were measured with extraordinary precision using NASA's Deep Space Network, tracking tiny shifts in the radio signal's frequency via the Doppler effect. By comparing the gravitational tug Io exerted on Juno at two different points in Io's orbit, at two different distances from Jupiter, the team could measure how much Io's shape changed between the two flybys. This measurement, called the tidal love number, quantifies how much a body deforms in response to tidal forces. A body with a global liquid layer just beneath the crust would deform a great deal. Its love number would be high. A body with a mostly solid interior, even one containing localized pockets of melt, would deform less. Its love number would be lower. The result was clear. Io's measured tidal love number was significantly lower than what a shallow, global magma ocean would produce. The data indicated that Io's mantle is mostly solid. There is melt inside Io. There must be given the volcanic output, but it is not organized into a single globe-spanning ocean of liquid rock. Instead, the picture that emerged from the Juno data is one of individual magma chambers, localized reservoirs of molten material that feed individual volcanoes or clusters of volcanoes, connected to the surface through their own plumbing systems, but not connected to each other through a shared liquid layer. Scott Bolton, the principal investigator for the Juno mission, summarized what the team found in direct terms. Since the discovery of Io's volcanism in 1979, planetary scientists had wondered whether a shallow ocean of white-hot magma fueled the volcanoes, or whether the source was more localized. The Juno data pointed firmly toward the localized model. This finding does not make Io's volcanism less impressive. If anything, it makes it more remarkable. A global magma ocean would have been a single, simple explanation for all of Io's activity. The magma ocean hypothesis had deep roots. It was not a casual speculation. It emerged from serious theoretical work and appeared to be supported by multiple lines of evidence accumulated over decades. Thermal models of tidal dissipation consistently showed that the amount of heat Io was producing required either an extraordinarily efficient mechanism for transporting heat through solid rock, which seemed unlikely, or a layer of melt that could convect freely and deliver energy to the surface rapidly. A global magma ocean provided that layer. It was thermodynamically elegant. Observational support came from the Galileo spacecraft's magnetometer. As Galileo flew through the space around Io, it measured how Io interacted with Jupiter's magnetic field. The data showed an induced magnetic signature consistent with a highly electrically conductive layer beneath the surface. Molten silicate rock is conductive. A global layer of it at shallow depth would produce exactly the kind of magnetic response Galileo detected. Several influential papers published in the early 2000s interpreted this evidence as strong support for the magma ocean model. But there were always dissenters. Some researchers pointed out that the magnetic signature could also be explained by a partially molten mantle, rock that was not fully liquid but contained enough interconnected melt to conduct electrical currents. Others argued that the thermal models were sensitive to assumptions about Io's internal structure and composition that were poorly constrained. The amount of melt required to explain the heat output depended on how efficiently that melt could reach the surface, and different assumptions about viscosity, permeability, and eruption dynamics produced very different answers. The debate continued for over 20 years, with neither side able to deliver a decisive blow, until Juno's gravity measurements provided the first direct constraint on how much Io's interior actually deformed under tidal stress. The measured Love number was too low for a global liquid layer at shallow depth. The magma ocean, which had shaped thinking about Io for 2 decades, was ruled out in a single measurement. One vast reservoir, one source, one system. What the Juno data revealed instead is that Io's tidal heating is powerful enough to independently create and sustain hundreds of separate magma chambers distributed across the entire moon. Each one is being maintained not by a shared underground sea of melt, but by the same external force, the tidal flexing imposed by Jupiter, acting on rock that is mostly solid, but being continuously worked, heated, and partially melted by the relentless orbital deformation. Picture what this means at the level of Io's interior. The entire mantle, thousands of kilometers of silicate rock, is being squeezed and stretched twice every orbit. Most of it remains solid, but the repeated stress generates heat throughout the volume. In regions where the heating is most intense, or where the rock is most susceptible to melting, pockets of magma form. These pockets accumulate, pressurize, and eventually find pathways to the surface. The result is a volcano. Not because a global ocean is pushing lava upward, but because the local rock in that specific region has been worked past its breaking point by tidal forces that operate everywhere, but produce melt in specific locations based on the details of Io's internal structure, composition, and stress distribution. This means Io's volcanism is not the product of a single geological mechanism operating in one layer. It is the product of a single external forcing, tidal heating, operating across an entire world and producing hundreds of independent geological responses. Each volcano is a separate wound in the crust, fed by its own source, opened by its own pathway, but caused by the same relentless gravitational punishment. The Juno data also refined our understanding of Io's internal structure. The gravity measurements confirm that Io has a large metallic core, primarily iron, extending to roughly half the moon's radius. Above the core sits a silicate mantle, and above that a thin crust, estimated at roughly 30 to 50 kilometers thick. The crust is continuously being produced by volcanic eruptions that deposit new material on the surface and consumed by a process scientists describe as crustal recycling, where older surface material is buried and pushed downward by the weight of newer deposits above it. This recycling is itself driven by the volcanic output. As eruptions pile new lava on top of older surfaces, the crust thickens locally, but the total volume of Io is not changing. The new material has to go somewhere. The older crust is pushed downward and laterally, compressed by the accumulating weight above. This compression generates its own tectonic stresses, which, as we will explore in detail later, produce some of the most extraordinary mountains in the solar system. But the point here is that even Io's crust is not stable. It is not a fixed shell sitting on top of a hot interior. It is a conveyor system continuously manufactured at the surface by eruptions, continuously consumed by burial and compression, continuously recycled back into the interior, where tidal heating can work on it again. The entire moon, from core to surface, is in a state of continuous mechanical processing, driven by the same external force. There is one additional dimension of the Laplace resonance that deserves attention, because it reveals just how precisely the trap is set. The resonance does not merely maintain Io's eccentricity, It also stabilizes the orbital relationships so effectively that the system resists perturbation. If some outside influence were to nudge Io's orbit, pushing it slightly out of the resonance, the gravitational coupling with Europa and Ganymede would pull it back. The resonance is not fragile, it is robust. It has persisted for an estimated 1 to 4 billion years, depending on the model, and there is no known mechanism operating in the current Jupiter system that could break it. Callisto, the outermost Galilean moon, is not part of the resonance. It orbits independently, too far from the other three to participate in the gravitational coupling. Some researchers have modeled scenarios in which Callisto is gradually drawn into a resonance with Ganymede over the coming billions of years, which would add a fourth body to the chain and potentially alter the dynamics. But that evolution, if it occurs, would take place over timescales so vast that they have no bearing on Io's current condition. For now and for the foreseeable future, the resonance holds. The trap is closed. It is worth pausing to consider what this means in plain terms. Io is a world roughly the size of Earth's moon. It is made of rock and metal. If it orbited Jupiter alone, without the gravitational interference of Europa and Ganymede, its orbit would have circularized billions of years ago. The tidal heating would have stopped. The volcanism would have ceased. Io would today look something like our own moon, grey, cratered, cold, dead. Its interior would have cooled. Its surface would have frozen in place. Impact craters would dot its terrain, undisturbed for billions of years. Io would be a museum piece, a quiet relic, unremarkable. Instead, because two other moons happen to orbit in the right positions, at the right distances, with the right masses, Io's orbit is trapped in an eccentricity it cannot shed. Its interior is trapped in a state of continuous heating it cannot escape. Its surface is trapped in a cycle of eruption and renewal it cannot stop. The violence of Io is not a product of what Io is, it is a product of where Io is. Place the same body in a different orbit, around a different planet, without the resonant companions, and it would be dead. But place it here, in this orbit, with these neighbors, locked into this resonance, and it becomes the most volcanically active body in the known solar system. The geology is not coming from inside Io, in the way that Earth's geology comes from inside Earth. It is being imposed on Io from outside, by a gravitational architecture that Io did not choose and cannot escape. That distinction is the most important idea in this entire story. Io's violence is not intrinsic, it is inflicted, and the system doing the inflicting shows no signs of relenting. But understanding the mechanism and understanding the result are two different things. The tidal engine explains why Io erupts. What it does not fully convey is what Io actually looks like as a world, what it feels like as a place, and how the combination of volcanic fury, crustal destruction, towering mountains, and environmental extremity produces a surface unlike anything else orbiting any planet we have ever studied. The surface of Io is not just active, it is alien in ways that challenge the basic assumptions scientists carry about what the ground beneath your feet is supposed to do. And it is that surface, in all its impossible detail, that reveals the true scale of what Jupiter's gravitational system has created. If you could somehow survive the approach, if you could shield yourself from the radiation sleeting through Jupiter's magnetosphere and descend through the thin wisp of sulfur dioxide that passes for an atmosphere, what you would see beneath you would look nothing like any world you have ever imagined. No oceans, No rivers, no forests or deserts or ice caps, no familiar geography of any kind. Instead, you would see a surface painted in violent color, plains of pale yellow and white sulfur, dioxide frost giving way to splashes of vivid orange, streaks of dark red, and vast fields of jet black volcanic glass. Those colors are not decorative. Each one is a chemical signature, a record of temperature and composition written directly into the ground. Sulfur is the artist, and heat is the brush. Elemental sulfur exists in multiple molecular forms called allotropes, and these allotropes shift depending on temperature. At typical background surface temperatures on Io, roughly 130 Kelvin in regions far from any active vent, sulfur dioxide frost dominates, producing the pale white and light grey expanses that cover large portions of the terrain. Where temperatures are slightly warmer, elemental sulfur in its most stable, crystalline form produces the vivid yellows that dominate the equatorial plains. As temperatures rise further, the chemistry shifts. Sulfur molecules transition from their 8-atom ring structure into shorter chains. These shorter chains absorb different wavelengths of light, producing the oranges and deep reds visible around active volcanic vents and in the deposits left behind by pelly-type plumes. The brilliant red rings that surround some of Io's most powerful volcanoes are composed of short-chain sulfur polymers. Molecules of 3 or 4 sulfur atoms condense from volcanic gases at specific temperatures. These deposits are ephemeral. Observations by the Galileo spacecraft showed that red plume deposits fade within months to a few years, as the short-chain polymers revert to more stable yellow forms. The colors on Io's surface are not just chemical indicators, they are clocks, marking how recently a given area was touched by volcanic activity. The blacks are different. The jet black deposits that fill caldera floors and spread outward from major eruption sites are not sulfur at all. They are silicate lava, cooled basaltic or ultramafic rock that are solidified after eruption. These dark deposits contrast sharply with the sulfur-dominated terrain around them, and serve as direct evidence of the high-temperature silicate volcanism that dominates Io's geological output. Over time, as sulfur dioxide frost and sulfur compounds accumulate on top of cooled lava flows, the black fades to grey and eventually disappears beneath the ever-present blanket of volatiles. The interplay between dark silicate deposits and bright sulfur coatings creates the patchwork of color that gives Io its distinctive, almost biological appearance. A surface that looks less like geology and more like an infected wound continuously forming and reforming its own scab. The terrain is flat in places, eerily smooth, as though someone had poured liquid across the ground and let it harden in layers. In other places, the landscape is broken by enormous dark pits, some of them over 100 kilometers across, their floors glowing faintly with the thermal signature of molten rock just below the crust. And rising above all of it, isolated and enormous, mountains taller than anything on Earth, standing alone without foothills or ranges, their flanks scarred by landslides so massive that the debris fields stretch for hundreds of kilometers. This is Io. Not as a data point, not as an entry in a catalogue of moons, as a place. The volcanic activity on Io falls into several distinct categories, and understanding the differences between them is essential to grasping the full scope of what this moon produces. Not all eruptions on Io are the same. Some are persistent and relatively quiet. Others are among the most energetic events ever observed on any solid body in the solar system. The first category is the lava lake. Io hosts multiple active lava lakes, volcanic depressions whose floors are covered in molten or semi-molten rock that persist for years, decades, and possibly centuries. Loki Patera is the most famous and the most powerful. Its dark, roughly horseshoe-shaped floor spans an area that dwarfs any comparable feature on Earth. Galileo images and subsequent ground-based observations revealed that Loki Patera undergoes periodic brightening events. Episodes roughly every 400 to 600 days, during which its thermal output surges dramatically. The leading explanation for these events is crustal overturn. The surface of the lava lake cools and solidifies into a thin, dark crust. Because solidified basalt is denser than the liquid magma beneath it, this crust is gravitationally unstable. Eventually it cracks along one edge and begins to founder, sinking back into the melt. A wave of overturning spreads across the lake at a rate of roughly 1 kilometer per day, exposing fresh incandescent magma as it goes. When the wave has traversed the entire floor and the old crust has been consumed, the process resets. New crust forms, it cools, it thickens, and eventually it sinks again. Detailed thermal mapping accomplished in 2015 when Europa passed in front of Io and allowed astronomers to isolate heat from individual volcanic sites, revealed that the overturning at Loki Patera was even more complex than expected. Not one, but two resurfacing waves were propagating simultaneously, sweeping across the lava lake floor from west to east. The temperature gradient across the surface increased smoothly in the direction of propagation from approximately 270 Kelvin, where the overturning had started and the new crust had already begun to cool, to approximately 330 Kelvin, where the overturn had most recently exposed fresh magma. But Loki Patera is not unique. Data from the GeoRAM infrared instrument aboard Juno, collected during the close flybys, revealed that hot rings of extremely high temperature surround the floors of numerous paterae across Io's surface. Loki, Soot, Amaterasu, Dajbog, and several others all display the same pattern. A glowing ring of exposed molten rock along the margins of the depression, where the cooling crust fractures and breaks against the patera walls, and a cooler central region where the crust is intact. This pattern strongly supports the conclusion that active lava lakes are not isolated phenomena on Io. They are a common and recurring feature of the Moon's volcanic landscape. The second category of volcanic activity on Io is the eruption-fed lava flow. These are events in which magma breaches the surface through fissures or vents and spreads outward across the surrounding terrain. Some of these flows are enormous. Ka ne he ki li fluctus, a massive flow field in Io's equatorial region, has been observed to brighten significantly in James Webb Space Telescope data, consistent with new lava being emplaced across its expanse. The Galileo spacecraft documented the appearance of an entirely new 400-kilometer wide dark deposit around Pilon Patera between two observation periods. Evidence of a major eruption that covered thousands of square kilometers of terrain in fresh volcanic material within months. These eruptions produce lava at temperatures and volumes that have no parallel on modern Earth. The erupted lavas are not only hot, but extraordinarily fluid. At the extreme temperatures measured by Galileo, the magma has a viscosity so low that it flows across the surface almost like water, spreading into thin sheets that can cover thousands of square kilometers before cooling enough to solidify. These are not the thick, sluggish lava flows familiar from Hawaiian eruptions. They are torrents of liquid rock that move fast, cover ground rapidly, and produce the vast smooth plains that dominate Io's terrain. The third category is the volcanic plume. Io's plumes are among the most visually striking features in the entire solar system. Because Io's surface gravity is low, only about 18% of Earth's, and its atmosphere is negligibly thin, volcanic gases and fine particles ejected from vents can reach extraordinary heights. Two classes of plume have been identified. The first, named after Prometheus, the volcano where the type was first characterized, consists of relatively small, persistent plumes reaching roughly 100 kilometers above the surface. These plumes are driven by the vaporization of sulfur dioxide frost on the surface when advancing lava flows pass over sulfur dioxide-rich terrain. They are essentially the product of lava boiling the ground ahead of it. The second class, named after Pel-A, one of Io's largest and most powerful volcanoes, consists of towering eruption columns that can reach over 300 kilometers above the surface. These plumes are driven directly by volcanic gases escaping from the magma itself during explosive eruptions. They deposit vast rings of red and orange sulfur compounds across hundreds of kilometers of surrounding terrain, creating the vivid bullseye patterns visible in spacecraft images. The Pel-A-type plumes are the ones that were first spotted by Linda Mora Beto in the Voyager 1 data. One of the most extraordinary plume observations in the history of Io science came not from Voyager or Galileo, but from a brief encounter by a spacecraft that was merely passing through. In late February of 2007, NASA's New Horizons probe, on its way to Pluto, conducted a flyby of the Jupiter system for a gravity assist. As it departed, its cameras captured a 5-frame sequence of the Tu-Vashtar volcanic region near Io's North Pole. The sequence, taken over an 8-minute period, showed a giant Pele-type plume erupting from the Tu-Vashtar caldera, climbing approximately 330 kilometers above the surface. The plume was so large that it was clearly visible against the blackness of space beyond Io's limb. A fountain of gas and fine particles rising to an altitude higher than the distance between Washington and Boston, powered by nothing but the pressure of volcanic gases escaping from Io's interior into the near vacuum above. The New Horizons images captured something else that made the sequence scientifically invaluable. The plume was not a simple vertical column. It displayed complex internal structure, with filaments and density variations visible within the erupting material. The images revealed that the plume was being fed by multiple closely spaced vents within the Tu-Vashtar caldera, each contributing its own stream of ejecta to the combined structure. The observation provided direct evidence that large Ionian eruptions are often fed by distributed vent systems rather than single-point sources, a finding later echoed by the Juno team's interpretation of the 2025 Southern Hemisphere eruption as originating from multiple closely spaced hotspots above a connected subsurface magma chamber. They are also the ones that can reshape entire regions of Io's surface in a matter of weeks. Juno's December 2024 flyby may have captured plumes in action over Io's southern hemisphere, and the eruption announced in January of 2025, the most intense ever recorded on the moon, produced thermal signatures consistent with an explosive event of staggering power. The hotspot detected by the GEORAM instrument was so energetic that it saturated the detector. Alessandro Mura, a Juno co-investigator from the National Institute for Astrophysics in Rome, described what the instrument revealed. The data supported that the detection was actually multiple closely spaced hotspots erupting simultaneously, suggestive of a vast subsurface magma chamber system beneath that region. The combined energy output was 6 times the total output of every power plant on the planet Earth, radiating from a patch of Io's surface roughly the size of Lake Superior. This is a single eruption event on a single moon, and it is not unusual. The record before it was also held by Io. The record before that was also held by Io. No other solid body in the solar system is producing events at this scale. Now consider the mountains. Io's mountains represent one of the most striking paradoxes in planetary science. On a world defined by volcanism, the tallest structures are not volcanic at all. They are tectonic. There are more than 135 identified mountains distributed across Io's surface. They appear as enormous, isolated massifs, rising abruptly from the surrounding volcanic plains without foothills or chains. Their average height is approximately 6 kilometers. The tallest, Beau-Orsor-Lee Montes, reaches approximately 17.5 kilometers above the surrounding terrain, nearly twice the height of Mount Everest above sea level. Several of Io's mountains would rank among the tallest peaks in the solar system, if placed on any other world. These mountains are not built by erupting lava piling upward. They are built by compression. The mechanism connects directly to the crustal recycling process we covered earlier. As volcanic eruptions continuously deposit new material on Io's surface, the crust thickens. But the moon's total volume does not change. The newly deposited material buries older surfaces, pushing them downward. As older crust sinks, it is compressed laterally by the weight of the accumulating layers above. This lateral compression generates enormous tectonic stresses. When those stresses exceed the strength of the rock, the crust fractures along thrust faults, and massive blocks of older crustal material are shoved upward, often tilting as they rise. The result is a mountain. Not the gradual product of millions of years of uplift, but the violent expulsion of a crustal block forced out of position by the relentless pressure of volcanic burial. The process resembles a conveyor belt with a blockage. Material is continuously fed onto the surface by eruptions. It moves downward and laterally as it is buried. When it encounters resistance, or when the accumulated stress reaches a critical threshold, something gives. A block breaks free and is thrust upward. The mountain that results is steep, angular, and unstable. Many of Io's mountains show evidence of massive landslides on their flanks, debris aprons stretching for hundreds of kilometers, where entire cliff faces have collapsed under their own weight. The collapses are not gentle. When a cliff face on Io fails, it fails at a scale that has no terrestrial equivalent. The mountain Euboea Montes, standing roughly 10.5 kilometers high in Io's southern hemisphere, displays one of the most dramatic examples. High-resolution Galileo images revealed that the entire northern flank of the mountain had given way at some point in its history, producing an avalanche of rock debris that spread across the surrounding plains in a deposit estimated at approximately 25,000 cubic kilometers in volume. To grasp what that number means, consider that the largest known landslide deposit on Earth, the Markagunt gravity slide in Utah, involved an estimated 1,700 to 2,000 cubic kilometers of material. The Euboea Montes collapse moved more than 12 times as much rock, and this occurred on a world with a diameter less than 1/3 of Earth's. The cliff faces of Io's mountains are amongst the steepest and tallest scarps in the solar system. Beau-Orsor-Lee-Montes features a southeastern cliff face, reaching approximately 15 kilometers of near vertical relief. These are not weathered slopes. There is no rain on Io, no water erosion, no freeze-thaw cycling. The cliffs are raw tectonic surfaces, the exposed faces of crustal blocks that were shoved upward by compressive forces and left standing in the thin sulfur dioxide atmosphere, unsupported by foothills, surrounded by flat volcanic plains. Their steepness makes them inherently unstable. Seismic activity from nearby volcanic eruptions, or simply the ongoing tidal flexing that deforms the entire moon twice per orbit, can trigger catastrophic failure. When a 15-kilometer cliff collapses on a world with 18% of Earth's surface gravity, the debris travels extraordinary distances before coming to rest. The result is the sprawling aprons of shattered rock that surround many of Io's largest mountains. Geological crime scenes marking the moments when tectonic violence exceeded the structural strength of the crust itself. The estimated volume of the landslide deposit at the base of Euboea Montes, one of Io's larger mountains, is approximately 25,000 cubic kilometers. A mass of debris so large that it has no equivalent among terrestrial landslides. The mountains also appear in a geographic pattern that reveals something important about Io's geology. They tend to occur in regions where volcanic activity is less intense, and volcanic centers tend to occur in regions where mountains are absent. The two features seem to occupy complementary real estate on Io's surface. This is consistent with the compression model. In regions where volcanism is vigorous, the crust is thin and hot, unable to support the kind of brittle fracture needed to thrust up a mountain. In regions where volcanism has been less active, the crust has thickened and cooled enough to become rigid, storing compressive stress until it fails catastrophically, and a mountain is born. Io is not just erupting, it is being squeezed, fractured and thrust upward at the same time. The volcanic and tectonic processes are two expressions of the same underlying forcing. Volcanism is how Io expels heat. Mountain building is how Io's crust responds to the consequences of that expulsion. Neither process would exist without the other, and both are driven by the same tidal engine. Above the surface, Io possesses what can only generously be called an atmosphere. It is thin to the point of near absence, with a surface pressure roughly 100 million times lower than Earth's atmosphere at sea level. It is composed primarily of sulfur dioxide, and its density varies dramatically across the surface and over time. On the day side, where volcanic venting is active and solar radiation sublimates sulfur dioxide frost from the ground, the atmosphere thickens slightly. On the night side, and during eclipse when Jupiter blocks sunlight, temperatures drop and the sulfur dioxide freezes back onto the surface. The atmosphere partially collapses. Io's atmosphere is not a permanent envelope. It is a transient phenomenon, exhaled by volcanoes and condensed back onto the ground in a cycle that repeats with every rotation. The most dramatic demonstration of this impermanence occurs every time Io passes into Jupiter's shadow. Io's orbit carries it behind Jupiter for approximately 2 hours during each revolution. When the moon enters eclipse and direct sunlight is cut off, the surface temperature drops rapidly. The sulfur dioxide gas that had been sublimating from frost deposits on the sunlit surface loses its energy source. Within minutes, the atmospheric pressure begins to fall, the sulfur dioxide condenses and freezes back onto the ground, forming fresh frost on terrain that had been bare rock or warm lava just hours before. The atmosphere does not merely thin during eclipse, it partially collapses. Observations from ground-based telescopes and spacecraft instruments have confirmed that Io's atmospheric column density decreases substantially during these shadow passages, with some models suggesting reductions of 50% or more in certain regions. Then Io emerges from Jupiter's shadow. Sunlight strikes the surface again. The frost sublimates. Sulfur dioxide floods back into the space above the ground. The atmosphere reinflates, thickening over the sunlit hemisphere while remaining sparse on the night side. The entire process, collapse and reformation, plays out multiple times every week, tied to the rhythm of Io's 42.5-hour orbit around Jupiter. No other world in the solar system experiences anything comparable. Earth's atmosphere persists through night and day without measurable change in total mass. Even Mars, with its thin carbon dioxide atmosphere and seasonal polar condensation, does not undergo the kind of rapid, orbit-locked atmospheric collapse that Io endures. On Io, even the air is temporary. It exists at the pleasure of sunlight and volcanism, and it is revoked the moment either one is interrupted. The sky above Io is not a stable feature. It is another expression of the same impermanence that governs the surface below it. Nothing on this world is allowed to persist. The November 2025 observations from the James Webb Space Telescope added important new detail to this picture. For the first time, researchers detected neutral sulfur atoms in Io's atmospheric emissions, in addition to sulfur monoxide. These detections opened a window into the chemical processes operating in the space between Io's volcanic surface and Jupiter's overwhelming magnetosphere. The results showed that Io's atmosphere is being shaped simultaneously by two forces. From below, volcanic outgassing supplies new material. From above, Jupiter's magnetosphere bombards the atmosphere with energetic charged particles that break apart molecules, ionize atoms, and strip material away from the moon entirely. This brings us to the radiation environment, and it is here that Io's situation becomes not just geologically extreme, but physically hostile in a way that compounds every other form of violence the moon experiences. Io orbits deep within Jupiter's magnetosphere, the most powerful planetary magnetic field in the solar system. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's. It traps enormous populations of high-energy charged particles, primarily electrons and ions, in radiation belts that extend millions of kilometers from the planet. Io's orbit at approximately 422,000 kilometers from Jupiter's center places it squarely within the most intense region of these belts. The radiation dose at Io's surface is approximately 3,600 rem per day. For comparison, a lethal dose for a human being is roughly 400 to 500 rem delivered over a short period. Io receives roughly 7 to 9 times a lethal human dose every single day. No spacecraft has ever been designed to survive prolonged operation at Io's orbital distance. Every mission that has studied Io has done so during brief flybys, minimizing the time spent in the radiation environment. But the radiation does more than make Io inhospitable to life or technology. It actively participates in the destruction of Io's atmosphere and surface. Jupiter's rotating magnetic field sweeps past Io at a relative velocity of roughly 57 kilometers per second, because Jupiter's magnetosphere rotates with the planet's approximately 10-hour period, while Io orbits much more slowly. This creates an intense interaction at the boundary between the magnetosphere and the moon, one whose consequences extend all the way back to Jupiter itself. The bombardment of Io's surface and atmosphere by magnetospheric particles sputters material off the moon. Sulfur, oxygen, and sodium atoms are knocked free from the surface, and atmospheric gases, ionized by the radiation, and swept up into Jupiter's magnetic field. This process removes approximately 1 ton of material from Io every second. The ejected material forms a vast donut-shaped structure encircling Jupiter along Io's orbital path, called the Io plasma torus. This torus of ionized sulfur and oxygen is one of the most prominent features of Jupiter's inner magnetosphere. It glows in ultraviolet light. It influences the behavior of Jupiter's radiation belts, and it represents a continuous hemorrhage of Io's own substance into the space around it. But the plasma torus is not simply a passive ring of stolen material drifting in orbit. It is one of the most energetically significant structures in Jupiter's magnetosphere. The ionized sulfur and oxygen atoms from Io, once swept up by Jupiter's rotating magnetic field, are accelerated to enormous velocities. They circulate around Jupiter at speeds far exceeding Io's own orbital velocity, carried along by magnetic field lines that rotate with Jupiter's 10-hour spin. The result is a donut of superheated plasma, with temperatures reaching tens of thousands of Kelvin and higher in some regions, radiating intensely in ultraviolet wavelengths. The Io plasma torus is one of the brightest ultraviolet sources in the solar system after the star itself. The interaction also produces one of the most visually striking phenomena associated with Io. Jupiter's magnetic field lines that pass through Io act as conduits for enormous electrical currents, approximately 3 million amperes, flowing between the moon and Jupiter's upper atmosphere. Where these currents strike Jupiter's atmosphere, they excite atmospheric gases and produce glowing auroral spots, visible in ultraviolet and infrared images taken by the Hubble Space Telescope and by Juno's ultraviolet spectrograph. These spots are Io's auroral footprint on Jupiter. They move across Jupiter's atmosphere in concert with Io's orbital position, tracking the moon's location as it circles the planet. Io is one of the only moons in the solar system that leaves a visible, measurable mark on the atmosphere of the planet it orbits. The footprint has been observed to brighten and shift in response to changes in Io's volcanic output, confirming a direct physical connection between eruptions on the moon's surface and auroral activity in Jupiter's upper atmosphere. The relationship runs in both directions. Jupiter's magnetosphere does not merely receive material from Io, it also bombards Io's surface with the very particles it has stripped away, now accelerate to high energies and driven back toward the moon along magnetic field lines. This creates a feedback loop. Volcanic eruptions supply material to the plasma torus. The plasma torus feeds Jupiter's radiation belts. The radiation belts bombard Io's surface and sputter additional material into the magnetosphere. The moon is caught in a cycle of its own erosion, losing substance to a system that uses that substance to intensify the bombardment that causes further loss. Io is not just being heated and erupted, it is being eroded from the outside, atom by atom, by the same planet whose gravity forces its interior to melt. Jupiter squeezes Io from within through tidal heating and strips it from without through magnetospheric bombardment. The violence is not limited to one mechanism or one layer. It operates on every scale, from the deep interior where magma chambers form under tidal stress, to the surface where lava lakes overturn and mountains are thrust upward, to the thin atmospheric boundary where volcanic gases are torn apart by radiation. to the orbital space around the moon itself where ionized debris is swept into a plasma ring circling the planet. The 2026 study of Io's thermal output added one more dimension to this picture. Researchers analyzing GeoRAM data from multiple Juno flybys examined 32 of Io's approximately 400 paterae and found that previous estimates of heat emission had been systematically underestimating the contribution of cooler crustal regions. The central floors of lava lakes, even when not actively overturning, radiate significant thermal energy from crust that is still warm, typically in the 220 to 230 Kelvin range. Earlier studies had focused on the hottest features, the glowing rings, the fresh lava, the incandescent margins, and had used those measurements as proxies for total heat output. When the cooler but far more extensive crustal areas were factored in, the total thermal output of individual paterae jumped dramatically. One patera designated P63, previously estimated at 7 to 20 gigawatts of thermal emission, was recalculated at approximately 80 gigawatts when the full crustal contribution was included. Extrapolated across all of Io's volcanic features, the study suggested that the moon's total thermal output may be an entire order of magnitude higher than the canonical estimates that have been used for decades. If confirmed at the global scale, this would mean Io is not merely the most volcanically active body in the solar system. It would mean Io's volcanic output has been profoundly underestimated for the entire duration of the space age. The energy pouring out of this moon, generated by tidal flexing, transported through localized magma systems, erupted onto the surface, radiated into space, and stripped into Jupiter's magnetosphere, may be vastly greater than anyone appreciated. The researchers also used the thermal data to estimate the ages of the crustal surfaces in each patera. By plugging the measured temperatures into cooling models, they calculated that a crust at 200 Kelvin would be approximately 13 years old. Statistical modeling of the full dataset yielded a characteristic resurfacing timescale on the order of 8 to 10 years. Every decade or so, the surface of a typical lava lake on Io is completely replaced. The ground is not permanent. It is a temporary skin over a continuously active wound. Everything described here, every volcano, every plume, every mountain, every atmospheric cycle, every interaction with Jupiter's magnetosphere is happening simultaneously. Right now, not in sequence, not in episodes separated by quiet intervals. All of it, all at once, continuously, driven by the same tidal engine that has been operating since the Laplace resonance locked into place billions of years ago. Io does not have geological events the way Earth does. Earth has earthquakes, eruptions, storms, each one a discrete occurrence with a beginning, a middle, and an end. Io does not have events. Io has a condition. The volcanism is the condition. The mountain building is the condition. The atmospheric cycling and magnetospheric stripping are the condition. Nothing starts and nothing stops. The processes overlap, interact, and sustain one another in a continuous loop of geological violence that constitutes the fundamental state of the world. This is what makes Io unlike any other object orbiting any planet in the solar system. Other moons are active. Enceladus erupts water vapor through cracks in its ice shell. Europa's surface shows signs of ongoing geological renewal. Even Triton, Neptune's largest moon, displayed active geysers when Voyager 2 flew past. But on those worlds, the activity is localized. It is comparatively gentle. It coexists with vast regions of quiet, undisturbed terrain. On Io, there is no undisturbed terrain. There is no region that the violence has not touched. Every square kilometer of the surface has been built, buried, compressed, or blasted within geological moments. The violence is not a feature of Io, it is the identity of Io, and the deeper question, the one that changes how you think about what a moon can be, is what that identity means. What does it mean for a world to have no mechanism for peace? What does it mean for an entire geological existence to be dictated by a relationship the world did not choose and cannot leave? That question is not geological, it is something else entirely, and it is where this story has been heading from the beginning. Step back for a moment. Forget the numbers, forget the orbital mechanics and the infrared spectra and the Doppler measurements. Forget everything technical and ask one simple question. What kind of world is Io? Not what kind of world in the sense of its composition or its orbit or its catalogue designation. What kind of world in the sense of what it is like to exist, the way Io exists. Because across everything we have covered, across the resonance and the tidal engine and the volcanoes and the mountains and the stripped atmosphere and the radiation, one truth has been assembling itself quietly in the background. And it is a truth that changes how you think about moons, about planets, about what it means for a world to have an identity at all. Io is a world that cannot rest. That sentence sounds simple, it is not. On Earth, geological violence is real. Earthquakes devastate cities, volcanoes reshape landscapes, tsunamis erase coastlines. But between those events, there is stillness. Fields grow, rivers run, forests stand. The violence is punctuated by peace. It is the exception, not the rule. The default state of Earth's surface is stability. When something disrupts that stability, an eruption, a quake, a landslide, the system absorbs the shock and returns to equilibrium. That is how geology works on Earth. Disturbance followed by recovery, violence followed by calm, an event, and then a return to the baseline. Io has no baseline to return to. There is no equilibrium waiting on the other side of the eruption. The eruption is the equilibrium. The violence is not an interruption of Io's normal state. It is Io's normal state. When a lava lake overturns and exposes fresh incandescent magma, that is not a crisis. That is Tuesday. When a plume climbs 300 kilometers into the vacuum and deposits a ring of sulfur across a region the size of a country, that is not a catastrophe. That is how the surface maintains itself. When a crustal block fractures under compression and a mountain is thrust kilometers into the sky, that is not a tectonic event in the way the Earth experiences tectonic events. That is the crust doing the only thing it can do under the relentless pressure of continuous volcanic burial. On Earth, you can draw a line between ordinary conditions and extraordinary ones. Io has no such line. The extraordinary is the ordinary. The crisis is the constant. And this is not because Io is inherently more energetic or more unstable than Earth as a body of rock and metal. Io is roughly the same size as our moon. Its composition is silicate rock and iron. If you placed it in a quiet orbit around a modest planet with no resonant companions, it would be cold and dead and silent. The violence is not in the material. The violence is in the relationship. This is the idea that sits at the center of the entire story. Io's geological identity is not self-generated. It is imposed. Every eruption, every mountain, every atmospheric cycle, every atom stripped into Jupiter's magnetosphere is a consequence of a gravitational relationship that Io did not create and cannot modify. The Laplace resonance was established by the orbital evolution of the Jovian system over billions of years. Io did not choose to orbit where it orbits. It did not choose to be locked into a 4-2-1 dance with Europa and Ganymede. It did not choose to have its eccentricity maintained against every natural tendency towards circularization. These are circumstances imposed by the mass of Jupiter, the orbital positions of sibling moons, and the mathematics of gravitational interaction. The violence is the product of architecture, and the architecture was not designed. It emerged. There is something deeply unsettling about that. On Earth, we're accustomed to thinking of geological violence as arising from within. Our planet's volcanism is powered by its own internal heat. Our earthquakes are driven by our own plate tectonics. The energy comes from radioactive decay in the mantle and residual heat from formation. These are intrinsic properties. Earth's geology belongs to Earth. It is an expression of what our planet is. Io's geology does not belong to Io. It belongs to Jupiter. It belongs to the resonance. It belongs to the orbital geometry that forces the moon's interior to melt and its surface to erupt. If you remove Jupiter from the system, Io would go quiet within a cosmically brief period. The magma would solidify. The eruptions would cease. The mountains would stop forming. The atmosphere would freeze onto the surface and stay there. Io would become a dead world, indistinguishable in character from dozens of other small, rocky, cratered bodies scattered across the solar system. Everything that makes Io extraordinary is borrowed. Borrowed from a gravitational relationship that operates with mathematical precision and absolute indifference to the consequences for the body trapped inside it. This is what it means to say Io is violent because it is trapped. The word trapped is not a metaphor here. It is a precise description of the orbital mechanics. The Laplace resonance is stable. It has persisted for an estimated 1 to 4 billion years. It resists perturbation. No known mechanism operating in the current Jupiter system can break it. Io cannot spiral inward to escape. It cannot spiral outward to escape. It cannot shed its eccentricity. It cannot decouple from Europa and Ganymede. The system holds, the trap holds, and the violence continues. Compare Io with Earth one more time, but through a different lens. Earth's internal heat output is approximately 44 trillion watts. This heat drives plate tectonics, powers volcanic activity, and maintains the geodynamo that generates our protective magnetic field. But Earth's heat output is declining. The planet is cooling. The radioactive elements that generate much of the heat are decaying. The primordial heat from formation is slowly radiating away. In roughly 2 to 3 billion years, Earth's internal engine will weaken substantially. Plate tectonics may slow. Volcanism will diminish. The magnetic field may falter. Earth's geological vitality has an expiration date. It is a long date by human standards, but it is real. Our planet's violence is temporary, sustained by a finite reservoir of energy that is being spent. Io's heat source has no comparable expiration. The energy comes from Jupiter's rotation, transmitted through tidal interactions. Jupiter's rotational energy is so vast that the amount extracted by tidal heating of Io is negligible by comparison. Jupiter will not spin down enough to release Io from the resonance before the solar system itself is transformed by the death of the star at its center, billions of years from now. For any timescale that matters, Io's energy source is inexhaustible. The violence will not wind down. It will not cycle through a quiet phase. It will not gradually diminish as the moon ages. The forcing is external, and the external source is effectively permanent. This creates a situation that has no parallel among the planets. Every planet in the solar system that is geologically active is active because of its own internal energy, and the energy is finite. Mercury is dead. Our moon is dead. Mars is nearly dead. Venus may still be sporadically active, but its heat budget is declining. Even Earth, the most geologically dynamic planet in the inner solar system, is on a countdown. Among the moons, Enceladus and Europa are tidally heated, but their activity is gentler, more localized, and in the case of Enceladus, may be episodic rather than continuous. Io stands alone, not just as the most volcanically active body in the solar system, but as the only solid world whose geological violence is sustained by an effectively permanent external energy source operating at a level sufficient to continuously rework the entire surface. There is no other world like this, not in the solar system. And while tidal heating is expected to operate on some exomoons and exoplanets in other star systems, Io is the only example we can study. The only case where we can observe what happens when a world is subjected to this level of sustained gravitational punishment across billions of years. Io is not just a data point in the survey of solar system moons. Io is the proof that geological violence can be a permanent condition of existence for a world, not a phase it passes through, but the thing it is. That realization challenges one of the deepest assumptions most people carry about how worlds work. The assumption is that stability is the default, that moons are quiet places, that geological violence is something that happens to a world and then subsides, that given enough time, everything cools, everything settles, everything reaches a state of rest. Io demolishes that assumption. Io shows that under the right gravitational circumstances, a world can be locked into a state of perpetual unrest from which there is no natural path to peace. The violence is not a wound that will heal. It is the ongoing condition of existing in the wrong orbital neighborhood, and the scale of that condition continues to be revised upward. The 2026 thermal study suggesting Io's heat output may have been underestimated by a full order of magnitude is not just a correction to a number in a textbook. If confirmed globally, it means the gap between what we thought Io was producing and what Io is actually producing has been enormous. It means the tidal engine is even more powerful than decades of modeling suggested. It means the magma chambers beneath the surface are hotter, more pressurized, and more active than previous thermal budgets could account for. It means the surface renewal rate, the atmospheric cycling, the magnetospheric mass loss, all of it may need to be recalculated. The moon we thought we understood after 45 years of observation may be significantly more extreme than we realized. Future missions will refine this picture further. The European Space Agency's Jupiter Icy Moons Explorer, launched in 2023 and expected to arrive in the Jupiter system around 2031, will study the Jovian moons with a focus on Ganymede, Europa, and Callisto. Its instruments will also observe Io from a distance, contributing thermal and atmospheric data to the ongoing study. NASA's Europa Clipper, which launched in 2024 and is expected to reach Jupiter in 2030, will conduct dozens of flybys of Europa, but its instruments will also detect Io's volcanic emissions and magnetospheric interactions during passes through the inner Jovian system. A dedicated Io mission, the Io Volcano Observer, designated IVO, has been proposed and studied by NASA as a potential future Discovery-class mission. IVO would conduct close flybys of Io with instruments specifically designed to measure heat flow, map volcanic activity at high resolution, characterize the interior structure, and determine once and for all the total thermal output and the depth and distribution of melt within the mantle. As of the most recent mission selections, IVO has not been approved for flight, but the scientific case for it has been strengthened by every new dataset from Juno and Webb. The question is no longer whether EO deserves a dedicated mission. The question is when. What those future observations will find, nobody can say with certainty. But the trajectory of discovery over the past 45 years points in one direction. Every time a new instrument has looked at EO more carefully, it has found more activity, more heat, more complexity, more violence than the previous generation of data suggested. Voyager found eruptions that nobody expected. Galileo found lava temperatures hotter than anyone predicted. Juno found individual magma chambers, where a global ocean had been assumed. Webb found sulfur chemistry never previously detected. The 2026 thermal study found heat output potentially 10 times greater than prior estimates. The pattern is consistent. Every time we look more closely, Io is worse than we thought. Not worse in the sense of broken or failing. Worse in the sense of more extreme, more active, more committed to the geological violence that defines it. There is one more dimension of this story that deserves attention, and it is the dimension that is hardest to articulate in scientific terms, but may be the most important for understanding why Io matters beyond the field of planetary science. Io challenges the way we categorize worlds. In the common imagination, and often in the scientific literature as well, there is a hierarchy. Planets are important. Moons are secondary. Planets have geology. Moons are inert companions. Planets are dynamic. Moons are souvenirs of the formation era. This hierarchy is deeply embedded in how we think about the solar system, and it has been wrong about Io since the moment Voyager 1 arrived. Io is geologically more active than any planet in the solar system. It produces more heat per unit area than Earth. Its surface is younger than Earth's. Its volcanic output exceeds anything that Mars, Venus, or Mercury have produced in billions of years. Its mountains rival the tallest peaks on any world. If Io were orbiting the star at Earth distance rather than orbiting Jupiter, if it were an independent body classified as a planet, it would be considered one of the most remarkable geological worlds ever discovered. The only reason it is overlooked in popular accounts of the solar system is that it is labeled a moon. That label carries with it an assumption of subordination. Moons orbit planets. They are smaller. They are secondary. They receive reflected attention. But Io receives more than reflected attention from Jupiter. It receives direct physical punishment. Jupiter does not merely hold Io in orbit, the way a parent holds a child's hand. Jupiter squeezes Io's interior, forces its surface to erupt, strips its atmosphere atom by atom, and irradiates its terrain with lethal doses of charged particles. The relationship between Jupiter and Io is not one of passive gravitational companionship. It's one of active geological domination, and Io cannot leave. This is the element that transforms the scientific narrative into something deeper. A planet with violent geology is a planet expressing its own nature. An asteroid that is destroyed by a collision was in the wrong place at the wrong time. But a moon that is continuously, permanently, structurally prevented from achieving geological calm, a moon whose violence is sustained not by its own internal resources, but by the inescapable gravitational influence of the body it orbits. That is something different. That is a world defined by captivity. The resonance is the lock. Jupiter is the cage. Europa and Ganymede are the mechanisms that keep the lock from being picked. And Io is the body inside, endlessly producing heat, endlessly erupting, endlessly building mountains that will be buried and thrust up again, endlessly exhaling an atmosphere that will be torn away and replaced, endlessly losing pieces of itself to the plasma torus that rings Jupiter like a belt made of Io's own stolen substance. There is no rescue. There is no erosion of the system toward freedom. The orbital mechanics are clear. The resonance is stable. The energy source is permanent. Io will continue like this until something external to the entire Jupiter system intervenes, and nothing in the foreseeable future will. Every other geologically active world we know of is on a clock. Earth's clock runs for billions of years more, but it runs down. Enceladus may already be intermittent in its activity. Europa's ice shell renewal operates on timescales that allow for long periods of relative quiet. Even the most optimistic models of Martian geological activity place its final significant eruptions millions of years in the past. These worlds have trajectories that lead towards stillness. Io does not. Io's trajectory is a circle, not a spiral winding down, not a curve approaching an asymptote. A circle. The orbit repeats, the flexing repeats, the heating repeats, the eruption repeats, the burial and compression repeat, the stripping and replenishment of the atmosphere repeat. Nothing accumulates toward a resolution. Nothing converges on a final state. The system cycles, and the cycling is the point. If there is a single image that captures what Io is, it is not a photograph of a volcanic plume or a lava lake or a mountain. It is the orbital diagram. 3 moons circling Jupiter in a 4:2:1 ratio, locked in a resonance that maintains Io's eccentricity against every force that would eliminate it. The violence is in the diagram. The eruptions are consequences. The lava is a side effect. The mountains are collateral. The image that matters is the orbit, because the orbit is the sentence, and the sentence has no end. When we think about moons, we think about our own. We think of a grey, quiet world hanging in the night sky, reflecting sunlight, exerting a gentle tidal influence on our oceans, marking time in phases. Our moon is peaceful. Our moon is stable. Our moon, in its own way, is finished. It has completed its geological life. It has no story left to tell except the one already written in its ancient craters. Io is the opposite of that. Io has never been finished. Io will never be finished. Its geological story is not a narrative with a beginning, a middle, and an end. It is a loop, a continuous present tense, an eternal now of eruption and renewal, and destruction and rebuilding. Nothing on Io's surface lasts. Nothing on Io's surface is meant to last. The surface exists only to be replaced. The atmosphere exists only to be stripped. The mountains exist only to be buried and thrust up and buried again. Nothing is permanent except the impermanence itself. And the source of all of it, the reason it never stops, is not some mysterious force or exotic physics. It is gravity. Ordinary gravity, operating through ordinary orbital mechanics, produces extraordinary consequences because of the specific arrangement of masses and distances and resonant ratios that happen to exist in this one corner of the solar system. The most violent moon in the solar system is violent for the most fundamental of reasons. It is in the wrong place, at the wrong distance, with the wrong neighbors, and physics does the rest. Right now, as these words reach you, Io is orbiting Jupiter. It has been orbiting Jupiter for approximately 4.5 billion years. It completed its last full revolution roughly 42.5 hours ago. During that revolution, its body was stretched toward Jupiter and then released. Its interior was heated by the friction of that deformation. Magma moved through chambers in its mantle. Somewhere on its surface, lava was exposed to the vacuum. Somewhere else, sulfur dioxide frost sublimated into the thin, temporary atmosphere. Somewhere above its poles, Jupiter's magnetic field lines drove currents of 3 million amperes through ionized gas. Somewhere along its orbital path, atoms of sulfur and oxygen torn from its atmosphere joined the plasma torus, adding to the ring of Io's own lost material that encircles Jupiter like evidence of a crime that never stops being committed. And then the orbit completed, and it began again. The most unsettling thing about Io is not that it erupts. Many worlds erupt. It is not that it is hot. Many worlds are hot. It is not even that it is trapped, although it is. The most unsettling thing about Io is that it reveals a possibility most people never consider. That peace is not the natural condition of a world. That stillness is not the default. That a body of rock and metal, given the wrong orbital circumstances, can be forced into a state of permanent geological violence, from which there is no escape, no winding down, no final chapter of quiet. Io is the proof that the universe does not guarantee rest. It does not guarantee equilibrium. It does not guarantee that every world eventually settles. Some worlds are sentenced to motion. Some worlds are built to break. And some worlds, like Io, are not built to break at all. They are built perfectly well. They are simply placed in a system that will never let them stop. That is what makes Io the most violent moon in the solar system. Not the lava, not the plumes, not the mountains or the radiation or the plasma torus. It is the fact that the violence is structural. It is architectural. It is written into the orbital geometry of the Jovian system with the permanence of a mathematical law. And unless that geometry changes, which it will not, Io will continue. Erupting, resurfacing, losing itself, rebuilding, erupting again, a moon that cannot know peace, orbiting a planet that will never grant it.